Hello everyone. The headline of our lesson for today is classification of function and graphs. There is three main kind of function. Algebraic functions. It contained also polynomials, radical, rational, and absolute value function. Trigonometric functions. We will study sine, cosine, and tan. And exponential and logarithm function. For the first kind, algebraic function, we will start with polynomial. Also, for polynomials classified to many functions, the constant function is special case of polynomial of degree 0. Linear function is polynomial of degree 1, quadratic function polynomial of degree 2, cubic function polynomial of degree 3, and so on. For the constant function, as you know, the graph of it is horizontal line perpendicular with y-axis parallel to x-axis. And its equation is y equal a constant number, and the slope of this line is 0. For the linear function, the general form or the standard form of this equation is y equal ax plus b. A is the slope of the line and b is y-intercept. Either the slope will be negative and the line take this direction, or positive and the line will take this direction. For the quadratic function, the standard form is y or f of x equal to ax power 2 plus bx plus c. This is polynomial of degree 2. The graph of x squared is like this shape, open upward, and the vertex is at the origin. If x squared preceded by negative, then the shape will be open to the down and take this shape. This is x squared, this is negative x squared. If we want to draw x squared plus 1, then as you know, you have one unit vertical shape, one unit up down. If we want to draw x power 2 negative 1, then we have one vertical shape, one unit to the down. If we want to draw x plus 1 square, then it is horizontal shift, one unit to the left. If we want to draw x minus 1 all square, then it is horizontal shift, one unit to the right, like this. The vertex will be here at 1, 0, and take the same shape. Now, if we want to draw x minus 1 power 2 plus 2, then the transformation is one unit to the right and 2 unit upward. If we want to draw x minus 1 square minus 2, then the transformation is one unit horizontal shift, one unit to the right, and downward vertical shift downward 2 units. This is for the quadratic function. For the cubic function x power 3 is the special case of cubic function. Its graph is like this shape. If we want to graph x power 3 plus 1, then it will be shifted upward 1 unit, like this. This is 1. If we want to draw x power 3 minus 1, then it is vertical shift 1 unit to the down. If we want to draw x minus 1 power 3, then it is horizontal shift 1 unit to the right. It is like this. The inflection point would be at the point 1, 0. If we preceded x power 3 or x cubed by negative, then the shape will be like this one, from left to right, and the inflection point at 0, 0. For the radical functions, we will study square root function. The standard square root function is square root x. The graph of square root x is like this shape. The vertex at 0, 0 at the origin, and goes from the domain from 0 to positive infinity. If the square root preceded by negative, then we have a reflection by x-axis, then it would take this shape. Also, the vertex will be at 0, 0 and goes to the infinity, but the range will be from negative infinity to 0. If we add 3 to the x inside the root, then we have a horizontal shift 3 units to the left. If we subtract 3 from x inside the root, then we have horizontal shift 3 units to the right. If we replace the constant with the variable, instead of x minus 3, we write 3 minus x, then the domain will change. It will be negative infinity to 3, and the vertex still in 3 at 3, 0. But the domain will change. Here the domain is from 3 to infinity, but here the domain is from negative infinity to 3. If we subtract 2 from the square root, then we have vertical shift 2 units downward, as we studied before. If we add 2 to the square root, then we have vertical shift 2 units upward, like this graph. If we write 2 minus x, if we want to find the graph of 2 minus x minus 2, then the vertex will be at 2, 2, and vertical shift 2 units downward, as you see, and the domain is from negative infinity to 2, since the variable here preceded by negative. For the rational function, the standard rational function is y equal 1 over x. Its graph is 2 parts. Since 0 is not in the domain, then the graph separated to 2 parts, from 0 to infinity and from negative infinity to 0. Of course, 0 not is in the domain. If we multiply the function by negative, it will be negative 1 over x, and the graph will be reflected by y-axis. It will be like this shape. 1 over x squared is also one of the famous rational function. Its graph is like this. X-axis is horizontal asymptote, and if we multiply the function by negative 1 over x squared, the function will reflect it by x-axis. For the exponential function, the famous or the standard exponential function is e to the x. The graph of e to the x is take this shape. If we change the sign of the variable as e to the negative x, then the graph reflected by y-axis will be like this. If we change the sign of all the function e to the minus x, multiply f of x by minus, then the function will reflected by x-axis will be like this. If we preceded the function and the variable by negative, then the function will reflected by x-axis once and by y-axis one. Logarithm function, we will study the ln x. The graph of ln x is take this shape. When x is 1, ln 1 is 0. Here we have intersection point between the graph and x-axis. If the function preceded by negative, then we have reflection by x-axis like this. We reflected the graph by x-axis. If the variable preceded by negative, then we have reflection by y-axis. If the variable and the function replaced by negative, then we have reflection by x-axis once and by y-axis. Absolute value function. The standard absolute value function is absolute value x. The graph of absolute value x is like the letter B in English, vertex in the origin. If the absolute value preceded by negative, then it will be open downward like this, and the domain will be, the range will be from negative infinity to 0. If we add 1 to the variable inside the absolute value, then we have horizontal shift 1 unit to the left. If we subtract 1 from the variable inside the absolute value, then you have a horizontal shift 1 unit to the right. If we add 1 outside or any constant outside the absolute value, then we have vertical shift 1 unit upward. If we subtract 1, then we have down vertical shift downward 1 unit downward. If we preceded the absolute value by negative, then it will be open downward, and we add 1 here, then we have vertical shift 1 unit upward. The shape will be like this. If we have this function x plus 1 preceded absolute value x plus 1 preceded by negative, add to 3, then we have 3 transformations. The first one, horizontal shift 1 unit to the vertex. It will be horizontal shift 1 unit to the left. This is the negative 1. Then the graph will reflected by x-axis, and we have 3-unit vertical shift upward. Then the vertex will be at the point -1, 3, open downward. The graph of x minus 2 plus 1, then x minus 2, we have horizontal shift 2 unit to the right. This is 1, 2, the vertex will be at, and 1 unit vertical shift upward. The vertex will be at point 2, 1. If we have this function, absolute value, x plus 2 preceded by negative, minus 1 subtract by 1, minus 1, then the vertex will shift it horizontal 2 units to the left and reflected by x-axis and subtract 1 from it. It means vertical shift 1 unit to the down. Then the vertex will be at -2, -1. Example, use this graph to find the graph of the function y equal minus f of x minus 2 plus 1. Which one is the graph of this function where f of x, it has this graph? The function contains 3 transformation. Subtract 2 from the variable, multiply the function by negative, and add it 1 to it. F of x minus 2, it is horizontal shift 2 unit to the right, then the vertex will be at 0, 0 at the origin, preceded by negative, then we have a reflection by x-axis, plus 1, then we have a vertical shift 1 unit to the up. It is not this one because it's not shifted 1 unit to the upward, but we have this graph. It is its vertex at 0, its vertex is at 0, 1, but this one and this one, it is wrong since the graph shifted 2 units to the left, but we have x minus 2, it means the graph should be horizontal shift 2 units to the right. Sketch the graph of the function y equal x plus 2 with the domain -2, the set of -2, -1, 0, 1, 2, 3. Then I generate a table of points x, y, -2, -1, 0, 1, 2, 3. It's the domain. When x is -2, the function is 0. Substitute -2 in the function. When the variable x equal -1, then -1 plus 2, it's 1. When the x equals 0, then the function is 2, 1, 3, 2, 4, 3, 5. Then the graph will be the domain from -2, -1, -2, 1, 2, 3, and the range from 0 to 5. 1, 2, 3, 4, 5. The first point, -2, 0, it is on x-axis here. The second point, -1, 1, it is here. 0, 2, it is y-intercept here. 1, 3, this is 1, 3, 2, 4, and 3, 5. Just like this. Don't draw a line joining these points because the domain is not from -2 to 3 interval. No, the domain, it is set only these 6 points. Then the graph will be points on the xy plane. The last kind of special function is trigonometric function. We will study three famous trigonometric functions: sine, cosine, and tan theta. For the sine theta in a right angle triangle, the mathematician set sine theta equal to opposite over hypotenuse. If opposite is A and hypotenuse is C, then sine theta equal to A over C. How we make this graph for sine? In the unit circle, if we divide it to 4 quarters, then I can find different value to theta from these triangles. This value I set it here as theta and f of theta. The horizontal line is for theta and the vertical axis is for f of theta. We find different value here from the unit circle and generate a table of points, set it in xy plane, and we can make this graph. Cosine theta defined on right angle triangle as adjacent over hypotenuse, adjacent B over hypotenuse C. Also, it is periodic function, but it is even if we flip the right side by y-axis to the left side, then the two parts will match. Its periodic is 2 pi, from 0 to 2 pi, from negative 2 pi to 0 from the left. Its range from negative 1 to 1, like sine, also the range from negative 1 to 1, and the domain for both function, sine and cosine, is from negative infinity to positive infinity. For the tan theta, since it is equal to sine theta over cosine theta, then it is A over C. B, we can reduce B with B, then it will be A over B. Opposite over adjacent. Since cosine theta is in the denominator, and as you see, when theta is pi over 2, then cosine is 0. Therefore, we have at the value where cosine is 0, we have a vertical asymptotes. Therefore, at pi over 2 and 3 pi over 2 and negative pi over 2, negative 3 pi over 2, and so on, we have vertical asymptote. Since the denominator, this value make the denominator 0. And also it is periodic function. Its period is from 0 to 2 pi. The domain is all real number except those make cosine 0, and the range is all real number from negative infinity to positive infinity. I'll complete this lesson by studying the behavior of polynomials function. How we can know the behavior of polynomials when x tends to infinity or negative infinity. If the greatest power of x, we will lift all the terms in the polynomial and take the term with the maximum power, with the greatest power. if the greatest power is even and its coefficient is positive, the greatest power is even and its coefficient is positive, then when x tends to positive infinity, also f(x) tends to positive infinity. But when x tends to negative infinity, then f of x also tends to positive infinity since the power is even. As you know, negative infinity to the power n when the power is positive infinity to the power n when the power is odd, it's equal to infinity, positive infinity, and when the power is even, also equal to power to positive infinity. But negative infinity to the n when the power is odd, it's equal to negative infinity. But when the power is even, it's equal to positive infinity. Here, x tends to negative infinity, but the power is even, then it is equal to positive infinity. And since the coefficient is positive, then the answer is infinity. If the greatest power of x is even and its coefficient is negative, then x tends to infinity, then f of x tends to negative infinity. Since it is infinity multiplied by negative number, then f of x tends to negative infinity. X tends to negative infinity, then f of x tends to negative infinity also, since negative infinity to the even power will be infinity times a negative number, the answer will be negative infinity. If the greatest number of x is odd and its coefficient is positive, then x tends to infinity, f of x also tends to infinity, since the positive infinity, it's equal to infinity in both cases, n is odd and even. X tends to negative infinity, then f of x tends to negative infinity, since the coefficient is positive. The last case, if greatest power of x is odd and its coefficient also is negative, then x tends to positive infinity, f of x tends to negative infinity, since the coefficient is negative, and x tends to negative infinity, then f of x tends to positive infinity, since negative by negative times negative equal to positive. Let us solve some examples. Which one satisfy these two conditions? F of x tends to positive infinity as x tends to infinity, to positive infinity. F of x tends to negative infinity as x tends to negative infinity. Let us check one by one. Here, the x with the greatest power, it's 2x power 3. As x tends to infinity, infinity power 3, infinity, times 2, it's also infinity. The first condition satisfied. For the second condition, x tends to negative infinity power 3, it is negative infinity, times positive coefficient times 2, it is negative infinity. Then when x tends to negative infinity, f of x also tends to negative infinity. This choice is true. Let me check this one for you. When x tend to positive infinity power 2, it is positive infinity, times negative 3, the answer is negative infinity. Then f of x tends to negative infinity, not to positive infinity. It is wrong. For this one, when x tends to positive infinity, infinity power 3, it is infinity, times negative The answer is negative infinity, not infinity. Then this choice is wrong also. For the third one, when x tends to infinity, infinity power 2 infinity times 3 infinity, this is true for the first one. But for the second one, x tends to negative infinity power 2, it is infinity, times 3, also infinity. Then when x tends to negative infinity, f of x also tend to positive infinity. Also, this choice is true. Then the right choice is number 8. Which of these polynomials satisfy these two conditions? F of x tend to positive infinity as x tend to positive infinity. F of x tend to positive infinity as x tend to negative infinity. Let us check one by one. Infinity power 5 infinity, then x tend to infinity, f of x also tend to infinity. Negative infinity power 5, it is negative infinity. Then when x tend to negative infinity, f of x also tend to negative infinity. Then this function not satisfy the condition 2. Let me check this one. Infinity power 6 infinity times negative 2 negative infinity. Then when x tend to infinity, f of x tend to negative infinity. This function not satisfy condition 1. For C, infinity power 3, it is infinity times negative infinity, also not true. For the fourth one, infinity times 4 infinity, no coefficient, coefficient is 1, also is positive. Then when x tend to infinity, f of x also tend to infinity. When x tend to negative infinity power 4, it's infinity. Then x tend to negative infinity, f of x also tend to negative infinity. This choice is the right choice. Which of the following polynomials satisfy these two conditions? F of x tend to positive infinity as x tend to positive infinity. F of x tend to negative infinity as x tend to negative infinity. Infinity power 5 infinity. Then the first condition satisfied. Negative infinity power 5, it's negative infinity. Also the second condition satisfied. This choice is the right choice. Let me check this one. Infinity power 6 infinity times negative 2 negative infinity. Then when x tend to infinity, f of x tend to negative infinity. The first condition not satisfied. Infinity to the 5 infinity times negative infinity. Then when x tend to infinity, f of x tend to negative infinity. It is wrong. When x tend to infinity, infinity power 4 infinity, then f of x tend to infinity, the first condition satisfied. But the second condition, when x tend to negative infinity power 4, it is infinity. Then when x tend to negative infinity, also f of x tend to infinity. And this choice is wrong. The right choice is A. Another example. Which one of the following polynomials satisfy these two conditions? F of x tend to negative infinity as x tend to positive infinity. F of x tend to negative infinity as x tend to negative infinity. For the first one, when x tend to positive infinity power 5 positive infinity times 2 positive infinity. Then when x tend to positive infinity, f of x also tend to positive infinity. This choice is wrong. For the second one, infinity to the power 6 infinity times negative 2 negative infinity. Then when x tend to positive infinity, f of x tend to negative infinity. This condition is true. For the second one, x tend to negative infinity power 6 is even, then the answer is infinity. Infinity times negative 2 negative infinity. then when x tends to negative infinity, f of x tends to negative infinity, this choice is true also. The second condition is satisfied. For the third one, positive infinity to the 5 infinity times negative 2 negative infinity. Then when x tends to positive infinity, f of x tends to negative infinity is true. For the second one, x tends to negative infinity to the power 5 is odd, the answer is negative infinity, times negative 2, the answer is positive infinity. Then when x tends to negative infinity, this function tends to positive infinity, the second condition not satisfied. For the last one, infinity to the power 6 infinity times infinity, then the first condition not satisfied. The right choice is number B. Example, the last example in this lesson, which one is true? If f is a function, then f of ax equal to af of x. This is wrong because here the variable changed. The variable here is x, but the variable here is ax. This is true only when a is 1, but not for all real, and not it is not a rule. If we want to, if I want to give you an example, if f of x, for example, equal to x plus 1, then and a equal to 5, f and x equal to 3, for example, then f of ax equal to f of 3 times 5, 15, 15 plus 1, 16. But a f of x equal to a5, f of 3 equal to 5 times f of 3, 3 plus 1, 4, times 4 equal to 20. So it is f of ax not equal to a f of x. A vertical line can intersect the graph of function at most one. This choice is true. I said before, I explained that any graph of any function should intersect with the vertical line with only one point. If f of a equal to f of b, then a equal to b. This choice is also wrong because it is not necessary to the function, the image of any number in the domain to be unique. It also can a point in range to be image for two value in the domain. Here, f of a equal to f of b, but a not equal to b. So this is also wrong. It is possible for two lines with a positive slope to be perpendicular to each other. It's wrong since the two line, if the two lines are perpendicular, then their multiplication of their slopes should be -1, and two number multiply of two number to be negative, one of them must be negative. Then the right choice is number 2. See you next lesson.